section 14.4 or 14.5, depending on which section you're looking at. I'm going to call it 4.5. So 14.4 or 14.5, depending on, you'll see that in the homework. That would be, for Cal Poly students, is 14.4, for Pasadena is 14.5. Recall, if y equal f of u and u equal g of x, and you wanted to take a derivative of y with respect to x, y depends on u, and u depends on x, that's the chain rule. Or I could take this and put it right there, and take a derivative by taking the derivative of the outsidemost function times the derivative of the inside. Again, the famous chain rule from back in the days, if you remember. Something that never goes away. Now, we're gonna pump that up a dimension, and things are gonna look slightly different. Suppose z equal f of x, y, two variables. This is differentiable in terms of x and y, where x is a function of t and y is a function of t, then no harm done. It turns out to be those are both differentiable functions of t, then z is a differentiable function of t, and dz dt will be the partial of f with respect to the first variable, and by the chain rule, dx dt, and the partial of y with respect partial of f with respect to y, dy dt, the second variable. This is nothing more than your implicit. And if you try specifically implicit differentiation, that works. Literally, if you go by dz dx dx dt, that will work, plus dz dy dy dt. For one variable, not much difference, and I'll show you that. But for two variables, that's coming up. So for now, since all of those depend on the same variable t, if I want to take the partial of z with respect to t, and it has two unknowns, well, I start by the partial of z with respect to the first variable dx dt, again, plus I take the partial of z with respect to the second variable dy dt. And here you have a couple of options, and I'll show you both. So first you would say the partial of z with respect to t will be, what's the derivative of this with respect to x? Partial. Isn't that e to the x over y times 1 over y? And what would be dx dt? Cosine of t? Oh boy. Plus, what is the partial of z with respect to y? That's e to the x over y. The derivative of x over y partial with respect to y is negative x over y squared. And what is dy dt? That would be negative the sine of t. And there it is. Done deal. No harm done. If I was to say, why don't you find dz dt? Well, if you really want, you could do this. They're going to ask you to do that maybe at a given time. You could say, you know what? Since both of those are a function of, oh boy. Since both of those are a function of time, I could eliminate that process and put a sine of t right there and a cosine of t right there, and say, look, if I want to take the derivative of z, whether you take a partial or not, if there's only one variable, it doesn't matter, it's the same thing. that is the exponential, times the derivative of this, but isn't this really e to the tan of t? And what's the root of tangent? Secant squared of t. You could do that as well. If it's in terms of one variable, that really doesn't mean much. Now, if you clean this up, and I know that's a lot of cleaning to do, if you are to replace each of those x's by a sign, and each of those y's by a cosine, and simplify, you will get literally this. So, whether you do implicit like you do traditionally, or you just substitute in, it makes no difference. For a variable of t, it's the same thing. So if I take the partial of z with respect to t, again, that's the partial of z with respect to its first variable, because z is a function of x and y. So with respect to x times dx dt plus the partial of z with respect to the second variable, dy dt. So the partial of z with respect to t, the derivative of this partial with respect to x is the tangent of y. Derivative of that is 2t. Plus the partial of this with respect to y, x is a constant, that's secant squared of y, times the derivative of y, which is 1 over twice radical t. You're done right there. You leave it at that. You could also say, or you know what, forget all of this. I know that z equals x, which is t squared plus 1, the tangent of radical t. And I could say either the partial of z with respect to t, or dz dt. They're the same if it's only one variable. Product rule. Derivative of the first times the second, plus the first times derivative of the second. And guess what? If I was to go ahead to that piece right there and replace y by radical t, times 2t plus x secant squared of y, y is radical t, times 1 over twice radical t. And I'll notice, let me see if I messed up somewhere. Oh yeah, I didn't apply the chain rule. When I took a derivative of the second, I should have multiplied it by the derivative of the argument, which is the angle, right? So when I take a derivative of tangent, that's secant squared times 1 over twice radical t. And do you agree that this and that are exactly the same? So for one variable, it makes not much of a difference, but for two variables, it makes a massive difference. And let me demonstrate. So for one variable, you could get away with just replacing it or using the traditional implicit. But if I have a function in terms of x and y, and x happen to be a function of two variables, and y happen to be a function of two variables. So this is how we do it. We say f. F depends on an x and a y. When I want to take a derivative of partial of f, I'll take the partial of f with respect to the same variable, first one, the partial of f with respect to the second variable. And here now, I have x depending on two of those. I could take the partial of x with respect to t, or the partial of x with respect to t. with respect to u. Here I have two options as well. I could take the partial of x of y with respect to t, or I could take the partial of y with respect to u. And you just follow along and figure out which path you want. Normally, we're asked for one of those. For example, find the partial of z with respect to x, then you're really going to take, with respect to t, you're going to take this route. So here you're going to say the partial of z with respect to t is going to be, and it's all partial derivatives. That will be the partial of z with respect to the first variable, the partial of x with respect to t to match, plus the partial of z with respect to y, and you take this route, times the partial of y, and y depends on t because that's all they want. And what would that be? Partial of z with respect to t. Well, what's the partial of this with respect to x? The product rule. 1 over twice radical x times the sine of xy plus radical x times the cosine of xy times y. This is this times the partial of x with respect to t, that is simply 2ut, plus the partial of z with respect to y, that's a constant, that's the cosine of xy times x, times the partial of y with respect to t, that will be 3t squared. All of that mess will be my answer. Now, what if they want me to find the partial of z with respect to u? Well, the same deal, except I'm going to take this route, and I'm going to take this route. So I'm going to say the partial of z with respect to u is going to be, well, z depend on x, and x depend on u. Z depend on u, and z depend on the second variable, which is y, and y depend on u. And this will be the partial of z with respect to x. I already did that in the previous problem. You could copy that down. You could do it again. It's a good practice. The derivative of this with respect to x would be 1 over twice radical x times the sine of xy, derivative of the first times the second, plus the first times cosine of xy times y. That's this piece. The partial of x with respect to u is simply t squared. I didn't put parentheses here, did I? There we go. Not there. Oh boy, okay. I hit enter by mistake. Forget. I rearranged the problems a bit. So this right here is this right here, plus the partial of z with respect to y. Again, I cluttered this. The partial of z with respect to y, that's the square root of x times the cosine of xy times, with respect to y, that's x, times the partial of y with respect to u, that's negative 3u squared. I'm going to shift this just a bit, so I rearrange the furniture a bit. So I put them all on one line. And let me go ahead and do the next example. example B is right there. Let's do the same thing. Again, you don't need to do, if they ask for that on the homework to make a tree, you don't have to make a tree if you don't want to, but it does help a bit. So if I look at Z depends on X, and X depends on U and T. The other variable that U depend on is Y, and Y depend on U or T. It depends what you want. When they say find the partial of Z with respect to U, you're really taking this route. That is, the partial of Z depend on X. By the chain rule, X depend on U, plus the partial of Z with respect to Y, and that's where this would be helpful if you're having a hard time with this. They look like 2's, I apologize, that's actually a partial. I get carried away. With respect to U, the partial of Z with respect to U will be the derivative of this partial with respect to X is 1 over Y, times the partial of this with respect to U is the sine of T, plus the partial of Z with respect to Y is negative X over Y squared. The partial of Y with respect to U is radical T. Now if you replace X by all of that mess and Y by all of this mess, you will get the function in what you need, but this is a quick way of getting what we want. And if I take the partial of Z with respect to T, well, then you're taking this route. That's going to be the partial of Z. Well, Z depends on X, and X depends on T, plus Z depends on Y, and Y depend on T. So that would be the partial of this with respect to X is 1 over Y. That doesn't change. But the partial of X with respect to T is U, the cosine of T, plus the partial of Z with respect to Y is negative X over Y squared, times the partial of Y with respect to T, that's U times 1 over twice radical T. And that's sufficient for what we need. Now, really quick, what if I have 4 dimensions? If I want, and I'm going to do one of those. Let's say I want to do this. If I want to take the partial of W with respect to U, I'm going to start with the partial of W. There is no U in there. So I take the derivative of this with respect to X, the derivative of that with respect to Y, the derivative of that with respect to Z. And again, I apologize for those looking like 2's. That's really how they look like, a partial. Now, when I did this, I noticed that X depends on, and what do you want? You want everything in terms of U. And when you go to Y, by the chain rule, Y depends on U. And when you go to Z, you want the portion of Z only that depends on U. So the partial of W with respect to U is actually those values. So the partial of W with respect to X is the sine of YZ. The partial of X with respect to U is V squared radical R. The partial of W with respect to Y X is a constant, cosine of XY times, with respect to Y that's a Z, and the partial of y with respect to u is 3u squared, and the partial of w with respect to z, that is x. Lengthy problem, not hard, you just have to get used to it. Cosine of xy with respect to xz, with respect to z times x. Okay, I'm really messing this up. Here we go. Times the partial of z with respect to u, that is v squared r cubed. Alright. Now, if f of xy equals 0, unlike what I had before, if I have f of xy equals 0, then if I take the partial with respect to x of both sides, by the chain rule, this would be the partial of f with respect to x plus the partial of f with respect to y. And the derivative of a constant is 0. So if I solve for this, isn't this a 1? I get the partial of f with respect to y times dy dx to equal negative the partial of f with respect to x. And I'll get dy dx to equal negative the partial of f with respect to x divided by the partial of f with respect to y, which is negative f sub x over f sub y. That's very important if I'm given an equation. If I'm given everything on one side, 0 on the other side, it seems I could make use of that, and that's a very nice property to have. So, identically, I could say if I have z equal f of x, y, let me explain that a bit different. If I have ax plus by equals 0, and if I solve for y, wouldn't you say by equal negative ax, and y will equal negative ax over b? And if I take a derivative with respect to x, wouldn't that be negative a over b? Do you see how they switched? So, if I have a traditional problem and I want to take just dy dx, I could say e to the xy minus e to the y minus 1 equal to 0. As long as I get it to equal to 0, I'm matching this. And I could say, according to the rule, dy dx will be negative f sub x over f sub y, where this is f sub xy. That would be negative the partial of this with respect to x and the partial of this with respect to y. And that would be my answer. And if I wanted to do, again, this is already equaling to 0. If I wanted the partial of z with respect to x, I have y, z, and x. The partial of z with respect to x. Anytime you have more than two variables, you need partial derivatives. Wouldn't that be, by the same analogy, f sub x divided by f sub z, based on what I just found right there? What's the partial of this with respect to x? That's a 0. That is negative e to the y. That's it. The denominator, partial of this with respect to x, y times the root of natural log of z is 1 over z. That's a 0. Minus 2z. That's simple. And if I want to find the partial of z with respect to y, and I'll explain what that means. That's negative f sub y divided by f sub z. So the partial of z with respect to y will be negative. The partial with respect to y is natural log of z plus x e to the y over the partial of this with respect to z. It's right there. It's y over z minus 2z. The difference here, I'm not writing y as a function of u and v. So here they're in terms of just y and just z and just x, unlike what I had here, where I had x depend on two functions and y depend on two functions. If I'm just looking at dy dx, or the partial of z with respect to x, not with respect to u, I don't need that chain rule. And one quick use of this, here we are. We have the radius of a right circular cone. So we have one of these cones. There's the radius, there's the height. It says the radius of the right circle is increasing, so the radius, the RDT, is 3 centimeters per minute, while the height is decreasing at a rate of 5 centimeters per minute. What is the rate at which the volume is changing when R equal 100 centimeters and H equal 150 centimeters? Well, what's the volume of a cone? This part. My hand hits the interbar and it moves on. The volume of a cone is 1/3 pi r squared h. And if I take the partial of v with respect to t, right, which is really what they want. Actually, they want really dv dt. Now, I know you could do this implicitly. Let's use partial derivatives just to show you that does work identically. The pi over 3 is a constant. That's going to be, according to what I know, that's going to be the partial of v with respect to r, the first variable, dr dt, plus the partial of v with respect to h, dh dt. I know you could do this implicitly, and if you do it implicitly, you get the same result. And what's the partial of v with respect to r? Isn't that just 2rh dr dt plus what's the partial of v with respect to h? R squared dh dt. Notice if I did this implicitly, I'll get exactly the same thing. So if it's in terms of one unknown, which is time in this case, that's not a problem. But if I'm going to do the same problem in terms of two unknowns, and I don't know why they don't give us that here. Isn't that twice? I know what the radius is. The radius in this case is 100. The r dt is 3. R squared is 100 squared. Oh, I forgot the h. H was 150. And r squared is 100. And the h dt is negative 5. And the units for volume will be centimeters cubed per minute. And you could plug that in a calculator and figure that out. On a test, you could leave the answer like this. And that pretty much concludes this section.